In this video, I'll be going through some of the physics of musical instrument strings. In particular, I'll start off discussing engineering strain in unwound strings, then go on to engineering strain in wound strings. Then I'll discuss bends and what happens when you pull a string to the side to make a conventional pitch bend, or move a tremolo unit or vibrato unit on the guitar. And then lastly, in section 4, I'll discuss lump strings and how you can use lumps near the end of the sounding length of the saddle to correct for inharmonicity due to the stiffness of strings. There are links in the description which can take you to the different sections of this video, and also links to relevant journal papers. So let's start with the cylinder, which we will assume will be under tension T.
We have an L naught, and we have a little distance delta L. Okay, so L naught is going to be how long the sounding length was before we stretched it. Delta L is how much longer the string's got to make up the sounding length, and we call LF the result in terms of where the string ends up sitting on the supports at the bridge and the saddle. Okay? If you consider that bit of metal that ends up being the sounding length, what was it like before we moved the tuning peg? If you drew dots on the string at the point where it crosses the saddle at the start of the sounding length here, and draw a dot on the string where it's in the last of the nut before it joins the sounding length, if you looked at those dots, release the tension in the tuning peg, these dots would sag backwards a little bit. Measure the distance between the dots and you've got L naught. Okay, so we start off with a mass element which is going to end up being the entire sounding length of the string. It's not quite there yet. We stretch it and it ends up happening to be LF in length and under tension T. Okay, so that's the way to think about what happens to the actual mass in the string in painstaking detail. Now the tension should be equal to something called the Young's modulus times by the cross-sectional area of the string times by the delta L over L naught. Okay, so that's the definition of Young's modulus from our point of view. You may have heard of Young's modulus before or not, but E is Young's modulus, and it's commonly defined as being stress, stress over strain. So what is stress and what is strain? So strain is the engineering strain, which is the fractional extension. It's this bit in the bracket. So strain is defined as delta L over L naught, and stress is going to be tension divided by cross-sectional area. So that's the force per unit area. So we rearrange this equation and we get this. So we will call delta L over L naught the engineering strain. Engineering strain is dimensionless. It's a little length divided by a little length, so it's not going to have any units. T is in newtons, and A is in the meters squared. So E has units. So Young's modulus has units of newtons per meter squared, and force divided by area is pressure. So pascals is another way of saying newtons per meter squared. Okay, so that's our definition of engineering strain. Let's see what this means if we put that into the equations we already know for the fundamental frequency of a string, and that's where things get interesting. Okay, so tension equals that. Let's go on to our frequency. The frequency was equal to C over 2L. We know about that, and C is the speed of wave propagation along the string. So that's 1 over 2L times by square root of tension over mass per unit length. Okay, so what does that mean for these things? Instead of tension, I'm going to put in this formula: E A delta L over L naught. And instead of mass per unit length, I'm going to write A times by the volumetric density. Okay, why do I get away with that? Well, remember, delta V is mass over volume, and volume you can write as A times L, and therefore that's going to be rho L divided by A. Rho L, the mass per unit length, is equal to A times by the volumetric density, so that works. And this is where the magic happens. A cancels out the equation, and suddenly the diameter of the string doesn't matter anymore for engineering strain. So that should be ringing alarm bells, making you think that was unexpected, unless you've already seen this before, perhaps. Okay, so what we end up with is 1 over 2L square root of E times by engineering strain over L naught over volumetric density. And that is, the volumetric density doesn't change for different steel strings. And the E, the fundamental property that relates the stress and the strain for steel, is again a fundamental property of the material. The E doesn't change for different widths of string either. So both E and rho V don't change when you look at different unwound strings. So we can actually, from this equation, work out what the engineering strain is on the string given its sounding frequency and length. So rearrange that, and we've got 2L frequency squared, and then we multiply that by rho V over E. Okay, so that doesn't depend on the diameter. In other words, the distance that you turn the tuning peg to get a change in pitch doesn't depend on the diameter of the string. So that's the difference between tension and engineering strain. They're proportional to one another, but when you change gauges for a high E string from a 9 to a 10 to 11, you change the tension that you have to get up to pitch by, but you don't change how far you have to turn the tuning peg to get up to pitch. It's actually the same because the thicker string picks up the tension faster and ends up at a higher tension. The two things cancel each other out, and the distances involved don't depend on the gauge. So we need to define that in more detail and put in some numbers. Let's do it. So the A4 we define as being 440 Hertz. That's actually the 5th fret of the high E string. If you want to go down to the E string, E4, we would take that 440 and multiply by 2 to the power of 5 frets, well, yeah, 5 frets worth. So we actually do to the power of minus 5 frets over 12 to get our approximately 330 Hertz. 4 significant figures. Okay, so yeah, that's the pitch of the E string. You can see this is very close actually to a ratio of 3/4. So, what's the density of steel? Let's do this for steel. It's going to be about 7,860 kilograms per cubic meter. And E is going to be about 207 times 10 to the 9 pascals, or newtons per meter squared. Okay, so that's some numbers there. So what do we have for the engineering strain? For the high E string, we put in all the numbers. What's L as well? We need to have an L. That's just a tiny bit longer than 25.5 inches. That's a typical number for the length of a string on a guitar for something like a Stratocaster. Okay, so putting in these numbers into the equation, we can do that. Okay, so that's approximately 0.70% to two significant figures, so it's 0.0070 approximately. So what about, so this is high E. What about the other strings? If we go to the B3 string, this delta L over L naught, we could work out what that is. So and then G, we go for the G3 string. That's another 4 semitones lower. Sorry, 0.25%. Okay, so a lot less than half. That's the two significant figures again. Okay. Yeah, so this shows us what is happening on the strings. The high E string is stretched by less than 1%, and actually the G string is stretched by 0.25% of its length. So all we have to do to work out the actual distance that is pulled, delta L, and get delta L on its own, we just have to times that by a number of millimeters, 649 millimeters. We can multiply through to get delta L. So why don't we do that as well? So for the E4 string, delta L, that's going to be, we take our LF or whatever, or L naught, is approximately equal to LF, so this is an approximation, and multiply that by the delta L over L naught. So that's going to be approximately equal, because we're talking about tiny differences really. These numbers are a lot smaller than 1, so you know, it's like less than 100th of 1, these numbers, so we can use this approximation and get some decent numbers out for delta L. So that delta L is approximately equal to okay, and then B3 and then if you go to G3 delta L okay, so there are the distances involved, and these distances might be a bit surprising in that they're quite small. So what I'm saying is, if you take an ideal bit of steel and stretch it So it starts off with the length of the guitar string, about 25.5 inches, and then stretch it so it's 4.5 millimeters longer. That should be it already up to the sounding pitch E4. And if you take that same bit of steel and stretch it by 1.6 millimeters, it's going to have the final sounding pitch of G3. And that's irrespective, actually, of the width of the string. This is perhaps surprising. It's actually shown in the maths here and works in real life, but for the fact that, yeah, when you've got a real guitar, the real bit of string needs to be stretched before it's actually stable a little bit. So when people talk about stretching strings to get them ready to be in playing condition, there's a number of things going on. One thing that happens is the string needs to be bent around the supports so that it's nice and tight around the supports, like the saddle and the tuner. You don't want any slack there. If there's any slack in the tuner, it'll take a while to work its way out as you repeatedly play and stretch the string a little bit more. Also, the string, particularly high E strings, they're operating quite close to the point where the string will start to elastically deform. So you get what's called strain hardening. The string initially, if it's not been up to pitch before, will you put up to pitch and it just gets a tiny bit thinner and longer, and it loses tension, and then you need to tighten it again. And actually inside the structure within the metal, there are little dislocations that form and bind a little bit and strengthen the string a little bit. So you end up with the string being what's called work hardened. So that's part of what's going on when you initially are getting your string up to pitch. So that can be especially bad for very thin strings where you need them to strain hardening a bit as they're getting stretched quite close to the limits of what the material can take. And it can be quite bad for thick strings as well, especially thick strings if they're curving over the bridge initially instead of actually having a corner where they're going over the saddle. The string might bulge a little bit over the saddle, and it takes a while for the string to think, yeah, maybe I should be bending more at that point. And so initially you play the string and the string bends and sags and gets shorter and loses tension, and you tighten up the string again and it ends up being nice and stable eventually. So these numbers are closer to what you'll observe if you put on the string and then actually turn the tuning peg so that the string is getting shorter by 4.5 millimeters. That will make it go essentially completely flat to the point of being no tension. So this is about how much you would have to loosen the string by to get it slack again. For a G string, it's only 1.6 millimeters to get the string slack again after it's been tuned up and ready to go. Okay, so the reason we choose different tensions is to do with how much force it takes to put them onto the frets, which is obviously very important to the player. So there is an obvious reason for people being obsessed with tension, but engineering strain is an extra element to think about, which determines how much movement is required to get the strings to actually change pitch later on when you're moving a tuner or bending the string or using a tremolo arm. Okay, so we have this equation here which tells us for an unwound string what the engineering strain is going to be for a given frequency, for a given length of string. Given that we know what the material is made of, the volumetric density, and the Young's modulus, these things don't change when you're looking at different strings made of the same fundamental material. So we want to compare the mass in an unwound string with the mass in a wound string So in the unwound string, the mass is going to be just the cross-sectional area of the core multiplied by the length multiplied by the volumetric density, and that if it's an unwound string, it's only core that's there. And yeah, that's going to be like your pi d over 2 squared. Yeah. Okay, what if we are going to a wound string? It's going to change. So the mass for a wound string is going to be bigger, and it's going to be bigger by some factor, and we're going to call that factor tau for the moment, because you've got the volumetric density, but the string itself has got the cross-sectional area AC, but then it's got windings that are on top of that, and the windings are going to be adding to the mass, and we result in a bigger mass, and the factor by which the mass is bigger is going to be called tau. That's a factor which is going to be tau equals 1 for an unwound string, and tau is going to be greater than 1 for a wound string. Okay, so we can do maths to work out what tau should be for a given diameter of the core, and we could have a given diameter of the winding, called d subscript c and d subscript w. Even we could have more than one winding, all that type of stuff. So yeah, there is a formula in publication I've done, or 2 publications I've done on this type of topic, and we work out what tau is. I work out what tau is for a given combination of windings and core. Okay, so far this AC is assuming that the core is cylindrical. In real life, the core might be hexagonal. That's what I use when I'm specifying strings. I use a hexagonal core because it grips the windings better. Different cores are possible. Okay, so what's important for our point of view is that the mass on the string is going to be bigger than if you just considered the actual core by a factor, and we'll call that factor tau, and that factor tau is something we can vary by making the windings bigger. Okay, so yeah, this mass of an unwound string then, bear in mind we have to put into the equations what the mass per unit length is. Mass per unit length for an unwound string was volumetric density times the cross-sectional area of the string, which is the same as cross-sectional area of the core, whereas for the wound string, the mass per unit length is going to be the volumetric density and the cross-sectional area of the core multiplied by tau. So that's a bigger number. Okay, so that has an impact on the equations that we were doing earlier on. So we need to redo some equations. To take all that into account. And work out what frequency does. So frequency equals 1 over 2L times by square root of, and we have E A delta L over L naught over, and this time we've got a tau involved. Okay, so crucially, tau is not on the top of the equation because the cross-sectional area that's carrying the tension is the core. If our string is under tension, the tension's being carried by the core, and the windings are just spiraling around that. And yeah, if you compare a spring to a bit of steel of the same length, it's gonna, if you pull a bit of steel, a block of steel, and pull that to try and tension it, and compare that to the same thickness of steel being in a spring, like springs in the suspension are going to be a bit springy, whereas the block of steel of the same kind of thickness of steel in a straight line is going to really resist and create massive tensions that stop you from compressing it or stretching it. So yeah, geometrically, the mass of the winding going round the corners means that it doesn't carry any tension or negligible tension when you stretch the thing. Whereas the core is entirely responsible for the tension that we observe when we're playing a wound string and tensioning it and tuning it. So we don't have to take into account the cross-sectional area of the winding at all in the top half of this equation. This is the tension. Tension equals Young's modulus times by cross-sectional area of the core times by the fractional elongation here, the engineering strain. The bottom of the equation, the mass per unit length, is going to be the volumetric density times by not just the cross-sectional area of the core, but there's an extra factor bigger, the tau. The bigger the winding, the bigger the tau. Okay, so that gives us a control over the engineering strain. So if we rearrange this, delta L over L naught equals, again we've got 2LF squared, but this time we have tau times by rho naught V over E. The E we could give a subscript C as well, because actually the Young's modulus of the winding material doesn't matter. It's only, you know, the engineering strain of the core that actually matters here to work out the engineering strain. Okay, so it's no longer the case that wound strings are going to automatically have the same engineering strain irrespective of your choices as designing a string. When you're designing a string of a certain pitch and a certain tension, you can choose to have all core, in which case tau is 1, and no winding. Or you could choose to have a narrow core and a big winding, in which case tau is a lot bigger than 1. Not necessarily thousands, you know, it can't be thousands for a realistic string, but it could be bigger than 10 even, for your ratio of mass in the winding to the mass in the core. Okay, so you've got a big variation of delta L over L naught possible for the wound strings, because you can vary the ratio of the core width and the winding width. That means that you're varying how much the string stretches by to get it up to tension, and you vary how much you have to bend it to get it up to a new pitch. So in the next bit of the discussion, we'll go on and talk about what happens when you actually bend the string to the side into a triangle shape, say at the 12th fret, and see what happens. So say we've got our string, and our string initially is a straight line between the bridge and the nut. We take the string and we bend it onto the 12th fret, and it's going to be bent upwards by a certain distance. So let's call this distance y, and let's call this distance along here L, as before. Now, what we're doing there, we have made the string longer basically, and we're going to ignore for the moment the bit of string behind the saddle and the bit of string behind the nut. They have a small impact that is measurable, and you have to account for it if you want to be really, really accurate. But to give us a general idea of what's going on, we're going to use the first approximation of just ignoring the distances behind the nut and behind the saddle. So L is going to be the length of the string before it was bent. Once it's been bent into this shape, it's going to have extra length, and that's going to add to this number to determine how much the sounding length's been extended. So we're going to check out what's happened to the string in terms of distances. What's this distance up here? Well, that distance up here is going to be, let's call it L1 for the moment. L1 is going to be the square root of L over 2 squared plus y squared. Now, what happens to the length of the string? How much does it change? Well, clearly there's an L1 here as well. So that's we can add those two L1s together and subtract by L, the original sounding length of the string, and we can work out the extension due to the bending. So we'll call this delta B. Additional elongation due to bending. So that's going to be 2 lots of this minus L. Okay, so going up to the top of the board, delta B is going to be, right, 2 times this. We could bring in the 2 squared actually. So that's going to be L squared plus 2y, isn't it? 2y squared minus L. Or L square root of 1 plus 2y over L squared minus 1. There's different ways of writing it, which maybe looks a bit neater. It depends on your taste. Right, so that's the extension of the string there. Okay, so we're going to work out the tension when it's bent compared to the tension when it's not bent, and that is going to be E A C, and then we've got the delta L plus the delta B over L naught divided by EC AC delta L over L naught. So cancelling out, we get basically the delta L plus delta B over delta L, which in turn is just going to be a 1 plus a delta B over delta L. Now up here we can actually take the delta B equals L times this stuff and divide 2 by L to get this. And then just use that. So we know this and we know that, therefore we can work out what's happened to the tension. Now when we're making the string longer by pulling it to the side and making it slightly longer, the sounding length is essentially just our original L1 divided by 2. Or it's L1 actually, isn't it? It's L divided by 2. Which is approximately the same thing as L1. And so we need to be careful about that when it comes to understanding what the change is in frequency. So the important thing is that the frequency once it's bent, the frequency once it's unbent is actually going to be to do with the tension. Remember in our original definitions, the frequency was equal to C over 2L, which was equal to 1 over 2L times by square root of tension over mass per unit length. Okay, and so therefore, when we're bending the string, F is proportional to the square root of tension. Okay, so actually the bent frequency over the unbent frequency is that. Divide by sign doesn't extend that far. Delta L over L. Okay. So that's how we can work out the frequency of the string once it's bent compared to unbent. The interval, in other words, to which we bent the string, is entirely due to the first approximation, how we extend the engineering strain by bending the string. The fact that L1 is slightly bigger than L over 2 is negligible because, yeah, this is half of 649 millimeters, and we're just bending the string to the side by maybe up to 30 millimeters or something, but the actual change in length along the axis of the string is pretty small compared to this L over 2. Okay, so that's a formula which tells us about the numbers involved. Okay, so we're going to work out what happens when you bend the string to the side by 1 centimeter. And so this is taking the string and pressing it down halfway along onto the fret, and then bending it to the side by 1 centimeter, which is just a tiny bit bigger than the distance between strings on this guitar. Something like that. So it's ending up about here. Okay, and then this one is going to be a similar story. And this one bending about this much. So we get different distances of bend on these strings, and we want to explain that. So pulling them to the side by 1 centimeter. You can see the diagram here. This is the length of the string, which is 649 millimeters for a typical Strat type thing. So about 64.9 centimeters long, and we're pulling it to the side by 1 centimeter. It doesn't make the string 1 centimeter longer, though. It's a lot subtler than that. So what happens to the frequency? We've got this formula which tells us the frequency of this section of string between here and here is changed in its frequency, for frequency bent being a ratio with the frequency of the unbent string, given by square root of 1 plus the strain due to bending, given by this formula here, divided by the strain through which the string was stretched, this ratio of stretch to get it up to tension in the first place. Okay, now instead of just staying there in terms of frequency ratio. I know for a fact this is a bit less than the semitone, but yeah, how do we work out how many semitones, or how many percent of a semitone this is? That might be a good number to use. The cents, the number of percent of a semitone, something you see on tuners and such like. So yeah, if we're going to do that, we need to work out for a frequency ratio, how many octaves have we got? Well, if it was 1 octave, it would be times by 2. If it was 2 octave, it would be 2 times 2, so 2 squared. If it's 3 octaves, it would be 2 times 2 times 2, so 2 to the power of 3. So if we do the log to the base 2 of a frequency ratio, we get a number of octaves. So what we're going to do is log to the base 2 of FB over FU. That's a number of octaves. If we want to know what that is in semitones, it would be times that number of octaves by 12. And if we want to know how many percent of a semitone, it would be times by another 100. So that's cents. Percent of a semitone, this formula here. So let's do that. So 87 cents to 2 significant figures. Okay, so that's how much the pitch changes for the high E string when you pull it to the side by 10 millimeters or 1 centimeter. This is something which doesn't change for different gauges of high E string. If the E string, high E string is thicker, like 13, it's going to take more force to move it away from equilibrium by 10 millimeters, but you're going to get the same change in pitch of 87 cents. If you took 9 thousandths of an inch thick high E string, it'd be a lot lower tension, so it would be much easier to move it to the side by 10 millimeters. But if you did move it to the side by 10 millimeters along the 12th fret, you would get an 87 cents increase still. Same number of cents, irrespective of the gauge you choose. It's properties of steel. Okay, so let's do the same for the B3 string and see what happens. So 149 cents to 3 significant figures in this case, to the nearest cent. So this is showing us that if we do the same motion on the B string, we get a lot bigger pitch change on the B string. Okay, we get 1.5 cents, 1.5 semitones more or less. So 1.5 semitones almost for the B string, whereas it's less than 1 semitone for the high E string. Let's do it again for the G string now. To 3 significant figures. Okay, so yeah, doing these bends, the behaviour is clear. When you do the same movement on a G string, it's a lot easier to bend, and that's not, something to do with what gauges people choose. It's got a lot more to do with the fact that the steel is something which has a certain amount of stretch to get it up to tension. The G string is less stretch to get it up to tension, therefore it's more sensitive. It's more sensitive to bending. It's also more sensitive to going into tune as well when you have friction, or the string doesn't go back to exactly the same place at the supports. Okay, so yeah, this delta B number, it's interesting to know what the delta B numbers themselves actually are. So the delta B over L required, that we actually resulted from our Y of 10 millimeters. Let's just actually show you that number again. 0.3131 millimeters. Okay, so the distance of stretch required to put the string out on the G string by 226 cents, more than 2 semitones. The distance required, you have to stretch that string over its entire length by 0.31 millimeters. To tune a string up by whole tone or down by a whole tone, roughly you're going to be moving the actual string over the tuning pick by something like 0.3 millimeters to achieve that. When you've got engineering string, remember that was 2L frequency squared, and then we multiply by the volumetric density over the Young's modulus, and then we've got this thing called tau, which is on the top as well. Okay, so remember that tau was 1 for unwound, and tau is actually equal to the total mass of the string over the mass of the core. Okay, if you have a thick core and a thin winding like this type of thing, then that is going to be tau close to 1. Whereas if you've got a thin core and a thick winding, that's a rather extreme example, then tau is going to be a lot bigger than 1. Okay, so this is the D core and the D winding. And here's our little D core, and here's our big D winding. Okay, so this string here is going to be close to 1 for its tau, so we have a relatively low delta L over L naught. And a relatively low delta L over L naught is going to make it very sensitive. If, on the other hand, we have a thin core and thick winding, then that's going to mean that tau is a lot bigger than 1, and we're going to get a very big delta L over L, and therefore it's going to be more like this. It's going to be less sensitive to bending. Okay, so essentially, if we want equal tension and we want equal bendability, we want to make equal tension and equal engineering strain. So rather than worry about the fine details about the equations for the mass in a winding, there's quite a simple way of actually writing down the relevant and important aspects of the mass to this. So remember, tension equals E of the core times A of the core times by the delta L over L naught. So we want different strings, like the D string and the A string and the E string, the low E string. Maybe we want to have them with the same resistance, the same tension, and if you move them 9 millimeters to the side, we want them to have the same amount of pitch they bend through. How do we achieve that? Well, we want to match the tension, and we want to match the delta L over L naught, so they've been stretched by the same distance to get them up to pitch, and if you bend them to the side by the same distance, it's going to have the same overall impact. And remembering that the smaller the delta L over L naught, the more sensitive the string is going to be, and the more it's going to go sharp. So we want to match that, and want to match that for equal sensitivity to playing styles. Okay, so we want different strings with different windings and different mass per unit length. So with different URL to have same tension and same engineering strain at rest. And when I say at rest, I mean at the playing pitch. Okay, how do we achieve that? If this is the same, EEC is the same, so that's the property of steel. And that's going to be the same for these different strings, delta L over L, that's the same for different strings, that's what we want. Then AC has to be the same. The cross-sectional area of the core has to be the same. Then AC should be the same. Okay, so that's rather a long way of getting to this point, but what we see here is that one equation, and actually if we want the different strings to have the same sensitivity, then we want to have them having the same core thickness if they've got equal tension. Clearly you can't do that with the unwound strings, because for the unwound strings, the high E, the B and the G, if they have the same tension and the same diameter, they would all be playing the same pitch. So we can't do it for the unwound strings. But we can do it for the wound strings. So we could have a G string, which is that thickness. We could have a D string, which is essentially the same thickness of core. We could have an A string that's the same thickness of core, and an E string which is the same thickness of core. And just having little windings on this one, and bigger windings on this one, and bigger windings on this one. Okay, the windings should really be very, very close to touching. But anyway, you get the idea. We could have the same D core on all of these, and just have a small dW and a bigger dW there, and a bigger dW there. We'll call these D winding 2 and D winding 3. Okay, so that's what my standard strings are like on my standard 9s, for instance. We've got a round core here and a hex core there, which is going to be very, very slightly different core diameter, but pretty close because it's a hexagon, which is available in about the same size as the cylinder there. And then this DC for this hex core is the same exact number as the DC, the core width for the A string, which is the same exact number as the core width for the low E string. So that means that if I design the windings right, to have thicker windings for the low E, thinner windings for the A, and finer windings for the D, we can get the tensions the same, and if you get the tensions the same and the core size the same, the engineering strain has to end up the same for these 4 strings. There are fine details, as I said earlier, fine details about the distance of string behind the nut is one of the things which matters. And yeah, you can actually design strings which do that. When it comes to, so this is like your G string, your D string, your A string, and your E string. So this is the G3, and this would be G3, D3, E2, A2, E2, there's B3, and E4. And so these ones are going to be thinner. So these C smaller. And this one here is going to be smaller again. Okay, so these ones end up having the bigger engineering strain. G string has a smaller engineering strain, and then that's matched by these ones. So compared to normal strings, most manufacturers will have a thicker core for the E string than they have for the D string. And that means that for most brands of string, when you bend the D string, it's going to take more distance of, the Y is going to be bigger to get a whole tone on the D. And Y is going to be smaller, very small, to get a whole tone on the low E string. Okay, so that's just choices about how to make strings. So one of the lessons is that the actual gauge of a string doesn't tell you everything about the string in terms of how it's going to respond once you bend it. Let's get out the guitar and have a look at the tremolo system. So when we take the tremolo arm, play G string, pull it up, the string's going to go up when you move this. So the tremolo arm is kind of a misnomer. It's really more of a vibrato arm in as much as it can make the pitch change. Vibrato is the word for when you rotate, shake the pitch or frequency of a sound. Tremolo is, strictly speaking, a variation in volume in most language, but when it comes to Leo Fender designed this type of design, having the springs in the back, and we play and pull, and it rotates the bridge to make the string mainly go sharp when you pull up without changing the height above the pickup that much. When we press on the bar, we can make the string dive as well. So that's movement of this arm makes these things happen. So when you actually make pitch changes like this on the bar, you can play a chord and then pull up the bar. You can see that it's not a nice chord anymore on the unwound strings when you pull up on the bar. And that's true of lots of strings in general on the Strat, but with my strings I've engineered the engineering strings to be the same. When you're moving the tremolo arm, the main thing you're doing is actually adding in one of these delta B things, the extra length stretch onto the string. And in doing so, if the delta L's are the same for the different strings, you should get pretty close to the same intervals when you move the tremolo arm. There are subtleties. Specifically, the bridge is a bit of curvature, which means that the G string and D string tend to be stretched by slightly greater distances than the low E string. So, yeah, I compensated for that. I've also compensated for the distance of string behind the nut. Yeah, the result, when you get all that right, so these engineering strings are about right, you can actually pull the bar and get a nice chord. So there's the unbent position. And that's it bent up a tone, and it's still a good chord. Right, so the last thing to talk about for the moment is going to be stiff strings. If you imagine a thick steel bar and you try and bend it, it's going to resist quite forcibly. Let's do F for the Pth mode is equal to, and then we're going to have P times F naught. So F naught is what the fundamental frequency would have been if we weren't accounting for stiffness, and then we've got a 1 plus b p squared, and all this is square rooted. Okay, so that's going to be a set of frequencies, P is going to be an integer number, 1, 2, 3, 4, and so on. If B was equal to 0, if P was equal to F0, and then 2F0, and then 3F0, and 4F0, and we've got a harmonic series. But actually, if we do the maths, we've got this extra thing called B, which might be non-zero, and then the frequency is going to get slightly bigger than P times F0. And as P increases, as the mode number increases, the frequencies are going to get more and more sharp. Okay, so what is B? B is a rather horrid looking thing. It actually goes as L to the power of 4, and it has lots of other stuff in it. Oh, L to the power of 4 is on the bottom. Sorry. So as L goes down, B gets a lot bigger if the length is smaller. That makes sense. So for we've got tau on the bottom as well, which is our difference between, and then we've got the U of the core, and the U of the core, basically AC rho subscript V, the volumetric density. What else have we got there? F0 squared as well. And what's on the top is pi squared, and then the E, and then the AC, and then the kappa squared, I think it is. Let's check that. Yeah, that's right. Okay, so that's the equations. Suffice to say, B is a small number, and we've got a bunch of harmonics which get sharper and sharper as we go up the harmonic series, but for guitar strings we can normally ignore that problem and we pretend they're perfect harmonics, even though they're very, very, very slightly sharp of a harmonic series as we keep going up, increasing P number. But for bass guitar, it's maybe a little bit more of a problem, and if you go up the neck on the guitar, you're making L go down, and whereas it's less obvious that open strings are inharmonic and have the harmonic series getting sharper and sharper, when you go to shorter string lengths by pressing down on the fret, you start to get higher and higher harmonics compared to the integer relationship that we expect from a nice sounding string. So how can we correct for that or change that? When I was first studying this topic, I figured that perhaps the fact that strings often have this taper for the low B string, for instance, where the string's really thick, I thought the taper maybe was helping with that, but I did the maths and checked, and it's actually kind of the other way around. So when you've got a string which is tapering, the idea is it goes over the saddle, it can bend over the saddle nicely, and then the string gets thicker for the rest of the sounding length. And that helps with getting the string to actually bend over the saddle. So that's called a taper, and it's got a lower mass here. So tau here and tau here. That tau is bigger, and that tau is smaller. Okay, so that's just adding extra layers of winding underneath before you put the layer winding on the top. You can make a tapered string. Okay, so that's something you can do. What does that do to the mode shapes and stuff? How does it change the relative pitch of the fundamental compared to the second harmonic, except it's not a harmonic? How does it compare the fundamental to the second mode, and so on? Well, the answer is we can draw some pictures and all that. So here's a fundamental frequency. If we consider a string which is vibrating at the same frequency but is a thinner string, the thinner string is going to have to be longer wavelength to actually have the same frequency. So you can imagine that this bit of string actually is extending the shape and changing the curvature of this if we're to consider one particular mode. Another thing we could consider is what happens if we do what I do on my strings sometimes, which is to add a lump on the bass strings. So we've got this string. What if we've got a string and we actually make it have a bigger cross section near the support? So if you've got a bigger cross section near the support, then this is actually going to mean that for the same frequency on this bit of string and this bit of string, this bit of string has actually got to have a shorter wavelength for the same frequency. So if we consider this one where we've got a tau big here and a tau small here, it's kind of an easier picture to draw intuitively. So what that means is we're actually making the shape get steeper when we get to here. So consider the string. This is tau constant along the length of the string. So it's got the same thickness of string all the way across. We get a nice sine wave for n equals 1. If we throw in the big lump, so we'll call this a lump string. And we've got tau big on this bit and tau smaller along there. Okay, so if we've got a lump string, the string goes along and does its thing, but at the last minute the string is actually doing the same frequency in this bit as that bit, but this bit here with bigger density, the bigger mass per unit length, is the same frequency that's got needs a shorter wavelength, and it's going to steepen. Okay, so it's as though the string has got longer. So zooming in on this bit of string, where the interesting stuff's happening, the string is coming down, and then for the thicker bit of string, it's actually getting steeper. And it's behaving like a longer string. Okay, so we found a way by adding a mass near the end of the string, you're actually making the string flatter. Okay, so this makes n equals 1 have a longer wavelength than it should if it was the same mass all the way along, or same mass per unit length all the way along. Okay, so that's what happens for n equals 1. What happens for n equals 2? For n equals 2, we are introducing a different frequency, which is basically doing this type of thing. And this time, instead of it starting very close to the end, I'm exaggerating the size of the lump here, but you get the idea. We're actually making it get steeper at an earlier point from higher up on the wave. And we are making it full, we're making the string appear to do a longer wavelength. It's doing a longer wavelength than it would if it was a unlumped string. Or p equals 1 if we want to use the same notation as before for this bit of talk. So p equals 1. This is p equals 2 for the second mode here. It's not a harmonic, it's a second partial, but we're making it closer to harmonic if we add a lump near the end, because essentially this lump is a bigger fraction of this thing here than it was here. It's actually, this lump is twice as big compared to the wave. That's going to mean that this is flattened more than this one. Okay, so we found a way by adding a lump near the end of the string. You make the modes flatter, but as you go up the series of modes, the flattening effect gets more pronounced. And that means that when you're dealing with a string which naturally wants to go sharper and sharper as you go up the harmonic series, if you add a lump near the end of the string, it's helping to flatten more and more as you go up the series. So for quite a number of the modes, you can get them much closer to being in a harmonic series. So when I'm designing my strings, I design lumps on my bass strings so that the second harmonic, even when you're playing up at the 21st fret, the second mode is a true 2 times the fundamental, instead of being sharper than that. So that's what the lumps are all about. So I've got the bass guitar here, and we can play a note on the low B string, and you get the P equals 2 there is going to be pretty much 2 times exact octave of the open, the unharmonicsed P equals 1 mode. And that goes for all the notes. Okay, so normally when you're way up the neck of the bass guitar, that will not be exactly an octave, it's going to be a bit sharper. So that's what the lumps are for. So yeah, playing them. That's the modes on the lump strings. Thank you very much for your attention. Do send comments and all that in the YouTube video, so thanks for your attention and see you another time.